So, let's dive into the fascinating world of aerodynamics, which plays a crucial role in understanding how airplanes fly. Basically, aerodynamics is the study of how air moves around objects, and it's essential for designing aircraft that can efficiently and safely take to the skies. First off, we need to understand the concept of airflow. Airflow refers to the movement of air around an object, such as an airplane. When an airplane moves through the air, it generates an airflow around its wings, fuselage, and other components. And this interaction between the air and the airplane surfaces is what creates the forces that allow it to fly. Now let's talk about pressure. Pressure is the force exerted by air molecules on a surface, and it's affected by the speed and direction of airflow. When air flows over a wing, it creates areas of high and low pressure above and below the wing. This pressure difference is what generates lift, the force that allows an airplane to stay in the air. There are four main forces acting on an airplane in flight: lift, weight, thrust, and drag. Lift, as I mentioned earlier, is the force that opposes the airplane's weight and keeps it in the air. Weight is the force of gravity pulling the airplane down towards the earth. Thrust is the force produced by the airplane's engines, which propels it forward through the air. And drag is the force that resists the airplane's motion, essentially acting as air resistance. Understanding these principles of aerodynamics is key to grasping how airplanes are able to fly. And it's amazing to think about the complex interplay of forces that allow these massive machines to soar through the skies. In the next sections, we'll delve deeper into the concepts of lift and thrust, which are crucial for understanding flight. All right, now that we have a good grasp on aerodynamics, let's explore the concept of lift, which is crucial for understanding how airplanes stay in the air. Lift is the force that opposes gravity, allowing the airplane to maintain altitude or climb to higher altitudes. It's generated by the interaction between the airplane's wings and the air around them. The shape and angle of an airplane's wings play a significant role in generating lift. Wings are designed with a curved, elongated shape called an airfoil. This shape causes air to flow faster over the top of the wing than below it. According to Bernoulli's principle, faster moving air has lower pressure, which creates a pressure difference between the top and bottom of the wing. This pressure difference generates lift, as the higher pressure below the wing pushes the aircraft upward. The greater the pressure difference, the more lift is produced. The angle at which the wing meets the airflow, known as the angle of attack, also affects lift. A higher angle of attack increases lift up to a certain point. However, if the angle becomes too steep, the airflow can separate from the wing, causing a stall and a rapid loss of lift. Another important factor in lift generation is the wing's aspect ratio, which is the ratio of the wing's length to its width. A higher aspect ratio typically results in more efficient lift generation as it reduces drag and allows for a smoother airflow over the wing. So, lift is a critical force that allows airplanes to defy gravity and soar through the skies. It's fascinating to think about how the clever design of wings and their interaction with the air around them can generate enough lift to keep these massive machines airborne. In the next section, we'll dive into the role of thrust, which works in tandem with lift to enable flight. Now that we've covered lift, let's move on to another crucial force in flight: thrust. Thrust is the force produced by an airplane's engines, propelling it forward through the air. This forward motion is necessary for lift to be generated, as the wings need to interact with the airflow to create the wings pressure difference we discussed earlier. There are different types of engines used in airplanes, but the most common ones are jet engines and propeller engines. Jet engines work by sucking in air, compressing it, and then mixing it with fuel. This mixture is ignited, creating a high-pressure exhaust that is expelled out the back of the engine, generating forward thrust. Propeller engines, on the other hand, rely on a spinning propeller to create thrust by accelerating air rearward. Thrust plays a crucial role in overcoming drag, which is the force that resists an airplane's motion through the air. As air flows around the airplane, it creates friction and pressure drag, both of which work against the forward motion of the aircraft. The engines must produce enough thrust to overcome this drag, allowing the airplane to maintain its speed and generate lift. In order to take off, an airplane needs to generate enough thrust to accelerate to a speed where the lift produced by the wings is equal to or greater than the weight of the airplane. Once in the air, the engines must continue to produce enough thrust to overcome drag and maintain a stable flight. So, thrust is a vital force in flight, working together with lift to keep airplanes airborne and moving forward. These powerful engines enable our aircraft to travel great distances and reach incredible speeds, connecting people and places all around the world. Next, we'll discuss the importance of control surfaces in maintaining stable and controlled flight. Now that we've explored lift and thrust, let's discuss another critical aspect of flight: control surfaces. These are movable parts of an airplane's wings and tail that allow pilots to manipulate the aircraft's altitude, pitch, and yaw, ensuring stable and controlled flight. We'll cover three main types of control surfaces: ailerons, elevators, and rudders. Ailerons are located on the trailing edge of each wing and control the airplane's roll, which is the rotation around the aircraft's longitudinal axis, running from the nose to the tail. When a pilot moves the control stick or yoke left or right, one aileron moves up, while the other moves down. This changes the lift produced by each wing, causing one wing to rise and the other to lower, resulting in a rolling motion. Elevators are found on the horizontal stabilizer, which is the horizontal part of the airplane's tail. They control the pitch of the airplane, which is the rotation around the lateral axis, running from wingtip to wingtip. When the pilot pulls back or pushes forward on the control stick or yoke, the elevators move up or down, changing the angle of attack of the horizontal stabilizer. This change in angle of attack affects the lift produced by the tail, causing the nose of the airplane to either rise or lower. Lastly, the rudder is located on the vertical stabilizer, which is the vertical part of the airplane's tail. The rudder controls the yaw of the airplane, which is the rotation around the vertical axis, running from the top to the bottom of the aircraft. When the pilot uses the rudder pedals, the rudder moves left or right, causing a change in the airflow over the vertical stabilizer. This change in airflow results in a side-to-side movement of the airplane's nose, known as yawing. Control surfaces are essential for pilots to maintain stable and controlled flight, as they allow them to make adjustments to the airplane's altitude, pitch, and yaw as needed. It's amazing to think about how these movements, relatively small surfaces, can have such a significant impact on the airplane's overall movement and stability. In the final section, we'll examine the principles of stability and how airplane designs incorporate features to ensure a smooth and safe flying experience. As we wrap up our exploration of flight, let's study the principles of stability and how airplane designs incorporate features to ensure a smooth and safe flying experience. Stability is crucial for maintaining controlled flight, and there are two main types to consider: static stability and dynamic stability. Static stability refers to an airplane's tendency to return to its original position after experiencing a disturbance, such as turbulence. Dynamic stability, on the other hand, refers to how the airplane responds to this disturbance over time, either damping out the motion or causing it to become more pronounced. One of the key design features that contribute to stability is the placement of the center of gravity, which is the point at which the airplane's weight is evenly distributed. By positioning the center of gravity slightly forward of the center of lift, designers ensure that the airplane has a natural tendency to return to level flight after a disturbance. If the center of gravity is too far forward or aft, it can cause the airplane to become unstable and difficult to control. Another important design feature for stability is the dihedral angle of the wings. This is the upward angle of the wings as viewed from the front of the airplane. The dihedral angle helps to increase lateral stability, as it ensures that when the airplane rolls to one side, the lower wing experiences an increase in lift, creating a rolling moment that pushes the airplane back towards level flight. Airplanes also rely on the natural stability provided by their tail section, which includes the vertical and horizontal stabilizers. These surfaces help to stabilize the airplane in the yaw and pitch axis, ensuring that it maintains a steady heading and altitude. In summary, the principles of stability are vital for maintaining controlled flight and ensuring a smooth and safe flying experience. Airplane designs incorporate features like dihedral wings and the careful placement of the center of gravity to achieve the desired level of stability. It's truly remarkable how these carefully engineered machines can soar through the skies, providing us with an incredible mode of transportation that connects us across vast distances